Thema, wie gesagt,
the virtual test environment at MTU Friedrichshafen.
Was machen wir bei MTU? Wir bauen Motoren, Dieselmotoren.
So what do? We build engines, diesel engines, gas engines for different application, maritime, mining, rail, fracking, military defense purposes as well. And all these applications have in common that we just deliver the engine and have nothing to do with the rest of the whole plant. So the classical driving test, as we know that of CV or passenger car, does not exist, which is quite clear. A 150-ton mining truck or a 100-meter yacht, we just don't get it in Friedrichshafen like that.
Das zweite Thema, was uns treibt, dass ein und derselbe Motor bei uns durchaus mit
The same engine that we build can be applied with different load profiles. The marine engine, for example, which is installed once in a luxury yacht, then it is also installed into a trawler in the harbor or into a boat that travels up and down the Rhine. And so there are different profiles to the application. And the broad range we service means that we have to take into account different regulations as far as emissions are concerned. There are 13 different regulations, ALMO, EPU, European legislation.
Ich habe hier mal so ein kleines
There is a characteristic map I brought along, and it shows in temperature and in altitude where we have to calibrate our machines. And you see few blue ones and a lot of red ones. The red ones are the ones we should need, and the blue ones are the ones that we can do on the test bench.
Das heißt, wir haben hier ein bisschen ein Problem.
So we have a sort of a problem here, so that we can calibrate the engines under these conditions. And for this reason, we have been doing simulation for many years where a lot of these characteristic curves are pre-calibrated.
Und das war für uns dann letztendlich die Entscheidung, okay.
And that decided as, okay, Simulink seems to be the platform we need. And it looks like this when you put it all together. The basic components are the engine and ECU model, as you can see here. And this system in-house is called MVP. And MVP stands for MTU Virtual Test Bench. And so you can have additional models, for example, a load simulation that may be a generator, it may be a ship model or a truck, but also the brake or just a driving curve. Then we have our cooling system. Cooling system is also extensive. We have several cooling circuits, maybe with seawater, and depends on the application. Then we have emission and exhaust after treatment. Here we're using various models as well. We are using partly physical models, but also DOE models, depending on what we want to do with this. And then we are showing the Inca SET, that is the interface between our Inca system, and that means that Inca interprets Simulink as a ECU. And all the parameters, I can then control them through Inca. Important in this setup is a standardized interfaces between the part models. As I said, on demand, we replace the engine model or the emission model, which works only if I have standardized interfaces.
Der Inca MVP.
The Inca MVP, that is the top tool which we give to our calibrating engineers. And it doesn't look spectacular. It's a laptop, and the calibrator looks at Inca. And MATLAB runs on the computer, and our Simulink model with engine, ECU, cooling, load simulation, and this is linked to Inca SEP, And the calibrator is working with the same tools. He's used to them from the test bed. So he's still working with Inca. The only thing that is added to it is load and RPM, speed. Otherwise, it's all the same. And he has the same interfaces to the subsystems, to Cameo. So with this virtual test bench, I can also do a Cameo automation, or I can exchange data sets with Krita. And Krita, that is how we manage our data sets and develop them. The next setup then would be the Puma MVP. So we have opened this up and have added a real test bed computer, which is the Puma Open, and we have a simulation of the Microsool, Smart Sampler, all the tools that you have. And of course, here as well, I can superimpose a Cameo. Inca is also used, and this gives me a 100% virtual test bench, which can be transferred one-to-one to the next test bench. So all the methodology I have, all the driving programs I develop, in a one-to-one ratio, I can also simulate it on my test bench.
Kommen zu meinem Beispiel. Auch hier
And now my example, and I've selected something which is not maybe every day. It is a small vehicle with a moderate load of about 160 tons. It's a mining truck in a mine in South Africa.
Und an dem Fahrzeug hatten wir das Problem, dass der beim Start und in einigen Fahrzuständen
And startup, we had soot development. Of course, this wasn't very nice. We didn't want to do it. There's smoke, there's soot production. Without performance loss, we wanted to reduce this, of course, because the mine operator is not very happy if we take his truck away for a week or two to do tests. So we entered the truck into our simulation, and then in this overall model, in connection with recordings we had of the truck, we have analyzed where's the problem to find where is the optimization potential, which we detected. And there was a bit of a conflict with transient functions with the transmission control unit, where there were a few hiccups, and we could solve this on our virtual test bench. So we have reprogrammed the transient functions, could evaluate it right away, and made a proposal for a data set on our virtual test bench for this vehicle. And then the engineer went to the mine, and he downloaded it and tested it, whether it works.
Das Problem konnte natürlich gelöst werden, sonst hätte ich es hier nicht mitgebracht.
Of course, we solved the problem, otherwise I wouldn't talking about it here to you. And we got positive feedback from the mine operator and from our test engineers. Originally, the test engineer was supposed to stay 4 weeks on site, and he did it in 1 week, and it worked very well. And as I said, the mine operator was very happy because we didn't use his truck for such a long time.
Was mir ganz wichtig ist, hier auch zu sagen, wir reden ja immer
Very important, we are always talking about how accurate do I have to have a model, and the last gram or the last ppm, do I detect it? In our environment, it's not necessary in very many cases. We need a qualitatively working model which shows the efficiency and mechanisms so that we can test our strategies and algorithms. If we want to calibrate, of course, then we need more accurate models. Then we select a different engine model and also emission models linked to that. But then the computing time is longer. Then we are in a factor 5 or 10 to real time. But that's all right. The computer does it overnight or the weekend. It's still better than burning hundreds of liters of diesel on the real test bench. And also, I can test functions at low risk. There is no risk that I destroy the engine. I see immediately it works, and I can also take countermeasures. Another important point in this virtual test bench we've done a lot of tests that we couldn't do on a real test bench because there was neither the time nor the money nor the technical equipment. And thus we learned a lot, especially in the methodology, how we can measure our engines even more accurately. And the fourth bullet point, simulation allows, without really having the application, the best adaptation of the engine to the truck, for example, or to the owner of the luxury yacht. The owner of the yacht wants a good propulsion of the yacht, wants his boat to be quicker than the neighbors, but he doesn't want any smoke. Ships are white. What is the biggest enemy of white? Soot, smoke. We don't like that. So we can do it in simulation without being in a harbor. And of course, in a very cost-efficient way, I can do my driving program testing and strategies.
Wir gehen wieder zurück in den Pkw-Sektor.
So let's return to passenger cars, and we're going to look at electronic control units again, ECUs in other words. So not just powertrain and engine, but actually all ECUs that you'd find in a car, and how these work together, and how we can verify and validate these systems in the future so that we can drive on the road. So the big challenge, what is it actually? Because even today we've been able to approve of ECUs. You remember, more and more big software systems are put into our cars, which means that the software V&V, which is verification and validation costs, are going to soar unless we do something about it. Unlike in the past, when we talk about highly complex systems such as are needed for automated driving or other cloud-based systems to verify them and validate them in the old ways, that won't work. We'll also see that software functions will no longer be focused on individual ECUs. So far we had engine control units which looked at engine functions, body electronics was in charge of light, for example. So we had a neatly ordered sort of world with different functions. That's going to change. Software functions are going to cut across several computer nodes. So how can we verify these functions and make sure that they will work in the field? It's a big problem that sometimes we cannot even describe the environment in which these functions run, at least not in isolation. That is why we call this the open world challenge. In automated driving, you can't possibly predict all the situations that will come your way. And what about our software solutions? How will they behave actually in situations which you haven't described or specified beforehand?
Heute haben wir die Situation, dass wir
Today, a lot of software systems have to be developed, compiled. Then we'll have executables, which we then download to the ECUs. And these ECUs then are put into Hill systems in order to carry out tests in this hardware-in-the-loop system. Because of this, we had to spend a lot of time carrying out sequential steps, and only once the software was released on the Hill system, it then was passed on to the OEM, who would then test it on board of the vehicle, only to find out that it didn't work together well with the car. It will be even more difficult if you have a system that's no longer a world of its own, that cuts across into other worlds, and that will have to change. So in the near future, therefore, we will have to use SIL systems, software-in-the-loop systems, which are completely virtual. So even the build process for our softwares will have to change. The build software will actually lead to executables, which are executable programs, and make them available, which can be run in purely simulated environment. And in these environments, you will not just have this one space of the ECU that's going to be simulated, but if possible, the whole environment of the vehicle, the whole of the EE architecture, all of the ECUs, the whole network, in order to find out whether all the functions which are part of this complex system really work. So very early on, we should be able to test software systems to such an extent that it will be much easier for OEMs in the future to integrate them in their own systems.
Und das, sagen wir, kann auch nicht ein einzelnes
And,
Unternehmen.
you know, it's not a single company, an isolated company that will actually be able to do this. Because if you look at the tier ones, there are several OEMs, let's say 5.
Die OEMs sehen aber, sie haben ungefähr
These OEMs, however, have 5 tier ones, perhaps. So,
Lösung schraubt.
if everybody works on their own solution, even within this relatively small group, we already will see a multiplication of possible solutions, 5 times 5.
Intern vielleicht auch nochmal so unterschiedliche
And I didn't even look at the different approaches which are sometimes pursued within one and the same company.
vorliegt und wir das nicht koordiniert in der
So, and unless we coordinate our approach, what we'll see is the rock here, this monolith on the right here, the monolith on the island of Rhodes. Monoliths which, you know, don't really help us and which are going to be extremely expensive, which is why we need to cooperate, so that we can exchange more, work more together at the interfaces, standardize interfaces in order to set up modular solutions and to integrate components from different systems. Well, standardization sounds as though it was something that was fraught with danger. Seems to be all about technicalities, but that's not why we want to standardize. First, we have to look at what it is we want to design. Of course, you can, for example, standardize the whole tool, which you can see on the right, but perhaps you only standardize the bits, which you can see on the left here. So that is what we need. So if the interfaces are right, we can use different kinds of tools.
Und wir brauchen auch ganz wichtig gemeinsame
And very importantly, we also need common solutions for co-simulation.
dass wir gemeinsame Lösungen haben, sonst
And what's important here is that we strive for common solutions. Otherwise, we'll be back to the old problem that we will have a wealth of different solutions.
eine sogenannte Silk Roadmap.
Well, and that is why we started to create a Silk roadmap at Bosch. Silk is actually software in the loop, common requirements of the automotive divisions of Bosch. Quite a mouthful. Silk is much simpler, of course.
Assoziiert man ein bisschen mit Indien.
And if you think of a roadmap and Silk Road, you think of India, perhaps.
Tief jetzt die Anforderungen an solche SIL-Environments.
So the requirements of SIL environments are to be captured across the different domains, and this specification will then be made available to the industry.
In die Diskussion mit ihnen zu gehen,
And we want to talk to you about it in order to find out how we could optimize these specifications.
wir werden dabei, jetzt ist wir tun etwas,
I think we've got a problem here with the mic and the sound. Anyway,
massiv nutzen.
of course, we're going to make the maximum use of the standards that exist, but we also will have to think about what we need these Silk environments for, which is why we are gathering use cases.
Für unsere SIL
So we've got an architecture for our Silk platform.
eine Architektur für unsere SIL-Plattform
We've got an architecture
oder aufgestellt.
which we already established for this platform. Well, it's just like you would actually do a software architecture.
Frameworks zu definieren.
So we're defining the requirements for it, and we're discussing it with the different divisions and also with industry.
Wir erhalten damit auf alle Fälle eine neue, effiziente Methode, Software
And this will also provide us with a new method to carry out software tests early on and not when it's late, when it's already incorporated in the customer's vehicle and there's no time anymore for iterative loops.
bieten wir an, von Bosch, dass
Which
wir
is why we from Bosch offer you
Spezifikationen mit Interessierten teilen, in eine
to share the Silk Road specification,
schauen, was
to discuss it with you,
auch von anderen beigestellt werden kann und
in order to also find out about what others might be able to contribute to it and how we can develop it further. Because we can only really achieve it if we work together on it. If everybody tried to do it in isolation, it will be incredibly expensive. And I think also tool manufacturers, of course, would be happy if they're not confronted and if they don't have to support such a wide variety of different solutions.
Mein Name ist Ralf Schmid von der Firma Knorr.
I'm Ralf Schmidt of Knorr-Bremse. Actually, we have a very similar task, hardware, software, combination test, and software in the loop scenarios for brake systems.
Also es würde für uns sicher erstmal ein sehr interessanter Ansatz sein.
Now, for us, of course, This is a very interesting approach, that is cooperating on it with other companies. Any ideas of how you might organize this? Well, actually, we're quite open as far as this is concerned, because we don't want people to get the sense here, big Bosch comes along and they're trying to impose something on us. I think it would make much better sense to just discuss it together.
Ich möchte Sie in den kommenden 20 Minuten
In the next 20 minutes, I would like to take you along on a journey which we started at ITES about 5 years ago, and Mr. Barbera was also part of this. And 5 years ago, as far as virtualization is concerned, we started with the FMI standard, and we did a tool development from scratch, which is based totally on the FMI standard. And now we have learned much more over time, and have developed the FMI V2 standard, which we integrate into our tools, and have realized a lot while we were on this journey.
So, aber heutzutage erleben wir eigentlich einen
And what we are seeing now is a boom in virtualization, and there are three main reasons for this. One is autonomous driving, the other is RDE, the real driving emissions, and the third are the acting processes.
Und dieser Schritt zu agieren,
The development process, and that is a very important step to take. And you have to realize, without virtualization, you will not be able to conduct agile development steps and processes, because agile development, that is early integration. And if you want to wait until the software is available on the hardware, then it's no longer acceptable. Several weeks ago, I heard a presentation by Daimler, and they introduced the term vilification, and that is exactly this. Before the software is running on the hardware available on the ECU, they want to integrate it and dial in a vilified powertrain. And that is this early integration I'm talking about. And so how can I do the IT steps? How can I protect my property with this integration issues?
und ich brauche eigentlich eine
And I need a test environment which does not only last till SOP as validation, but also after SOP, because continuously new software has to be downloaded onto the vehicle. And then another important trend which leads to it is that the importance of the domain architecture of the central computer will move validation issues.
So, und jetzt ist die Frage, wo ist die ETAS-Position?
Now, where's the ITES position in this? And I promised to take you on a journey with me, and it is important for us. A major statement at the beginning, and it says that networks are backbones. The EE architecture is the backbone into which I have to flange virtual ECUs. The network simulation, if I don't control the virtual networks, then I'm having a basic problem. And the eye-opener to me was the simulation of a single ECU is the exception rather than the rule. You have to think in the multi-ECU environment and then deduct what does it mean for individual virtualization, and not try to solve how can I do my individual ECU virtualization and then it is scaled up to several ECUs. Then the approach is not right. And this insight, we had it at the end of the year, last year, and we have this simulation backbone which is based on good network simulation. And not only that, I control a CAN bus, but the interaction between a FlexRay bus, an automotive internet bus, and a CAN bus together. So this interaction is very important. And synchronization is not solved in the models, but what this backbone provides as synchronization mechanisms. That was important for me to share with you, and all this is, of course, shown here, that our simulation architecture is in the center, that the backbone is clearly differentiated between our communication networks on the upper part and the signal networks on the lower parts, where you get signals from the models which have to be entered into the simulation and synchronized, independent whether I have a master self process and in the real world where everybody is doing his thing, and you have to separate it cleanly, that you have both variants. And this is, of course, not in an isolated world, but that we build prototypes. You have a use case here, which we are currently establishing together with Bosch. We are coupling various ECUs in the networks, and the interesting thing is not that this is technically possible. The interesting thing is that it's not a great software from research organizations that is coupled, but that we have here serious software. And it is a difference if I have a demonstrator or serious software and a Bosch chassis environment with a Bosch CM environment with a powertrain environment, that this will have to interact, and not as a prototype, but in the real software. And that means that your development processes, your make and build tool chains have to be adapted accordingly, because to create a virtual ECU is a special case, and you have to deploy to a real-time computer, to a cloud environment or something else.
Und benutzen heute eine Dockerized.
And we are using a Dopplerized or a Dockerized environment, which is a precursor. It has been existing since end of last month for Hill systems. And in the second half of 2018, it will be available. And then it doesn't matter whether you deploy it on your PC, on a real-time PC, whether you deploy it in a cloud. And with a cloud, I mean not a cloud provider, but a cloud IT model. There are various providers for this, but cloud is a model. It is not a provider. That is very difficult for many people to differentiate. And this is why at Bosch we have a Bosch on-premise cloud, where our automotive suite is running. And there it will seamlessly be integrated into our cloud.
Jetzt war die Frage.
Now the question was, how can ITAS help? And the one is the well-known thing that we help in the migration to a hardware platform, hardware-oriented way to transfer this to a virtual environment. And that's not only a tool issue, which is frequently misunderstood, but it's a question of architecture. And that means the investments, the business units who make the software, and how do I get the software portable? So what do I have to virtualize in order to cover my use cases? Is it basic software, or what belongs to this software that I run in my virtual environment? Then, of course, we will help you with the backbone for the SIL environment to integrate into this. We have front-loading of Hills in a Hill environment. With LabCar, with our LabCar COSIM environment, we offer this. Then we have the piloting of RDE. Mr. Kruse presented this today. That was frequently mentioned here, the real driving emissions in an open world, where we are closely cooperating with Bosch. Then we have the integration into these make and build tool chains. And last but not least, something that is in my department happening, that is big data, where we at ITAS focus on time series data, and of course with our offer the integration into video data and other data. And the last step, which is necessary, you have to, your simulation data, your results, you have to be able to analyze them just like the data that you gather in the field from the vehicle. So my takeaways at the end. First, the virtualization of systems is a necessary mastering control to develop virtualization processes, and we think that, especially with COSIM, we can only do it over the virtualization, then the backbone, because that is how you flange your virtual ECUs into the model, and then we have standardization. I think it is not attractive for OEMs if every OEM is having a separate individual standard, which is the case right now. And so that is neither a good business for the suppliers nor for the tool manufacturers, that except when you offer sheer services. And the last one is the integration of the virtual ECUs into your standards make and build environment. Very important, because otherwise it all remains theory, and you can have nice demonstrators, but the crux of the matter is to get it into our series development.
Wenn wir solche neuen Schritte gehen.
When we take these new steps, when we implement new methods and approaches, a lot is familiar from the Agile Automotive Conference 2 weeks ago, whether it's Jenkins or FMI, where we have to make people understand it's not the same developers, and we cannot fire them all and hire new ones and say the young ones will all understand it. What could be the process so that those who are nowadays in development, that they will also develop this emotion and this passion that you are showing here? Do you have any ideas how to do this? Well, I think there are these two visions. There is the mechatronic mechanical engineer, and there is the computer scientist talking about Docker, Jenkins, clouds. And I think the first misunderstanding is that they are living in two parallel worlds. No, they have to come together. And sometimes we act as if we don't need engineers anymore. There will be the e-powertrain, everything will be more simple. So this is a bit of teasing on the one side. But on the other hand, we have this interaction between software and mechatronics and the hardware. We have to understand it. And this is not gone overnight. But as far as agility is concerned, we can learn a lot from the software industry. And I think the software industry will be victorious in the cloud, in the domain main processes, and the engineers who are more in the embedded field. Now, how can you create the passion? By not being isolated, by inviting the others to come along in this. We are always isolated in different groups, and we don't have a platform also inside of companies, so that in a collaboration approach, these issues are reacted to from the idea side.